Hello, everyone. I'm Antonio and Michael here. We work for Mara Labs. We're building ZKSync. And today we'll be talking about our new upcoming protocol and prover. So before we do, let's start with a quick review of the current era of ZKSync's protocol. So ZKSync era was launched 2 years ago, and it was the first ZK EVM to hit mainnet. This required us to introduce a ZK-friendly custom VM, which we called Era VM. But this meant that we weren't 100% EVM equivalent, which proved to be quite a big pain point for both users and developers. Not only that, but it also meant that the VM that we use for smart contract execution was fully coupled with the proof system that we built. This is very annoying because every time we need to produce an upgrade to the VM, say introduce a new opcode or change the semantics or even fix a bug, it means that we need to go down into the circuits, which is complicated, dangerous, we need audits, and so on. And to make things even a little bit worse is we need two implementations for this VM, one for the sequencer and one for the proving. And they need to match perfectly, otherwise we're in big trouble. So still, this was a great achievement. 2 years ago, it was even a question if we could build this quick. But we've moved on. As ZKSync, we are no longer just Era right now. Instead, last year, we launched what we call the Elastic Network, which is a cluster of rollups using our technology. And each of these ZK chains require different needs. And as such, we need an elastic system that is easy to upgrade and customize. Also, we always need better performance, both for low confirmation latency in the sequencer, but most importantly, we need prover efficiency, cheap proving, and fast settlement. Right now, with all of the upgrades in this new protocol and proving system, we are at around 0.02 cents for proving cost for an ERC20 transaction. And by the end of the year, we want to get to half of that, but we're very confident that we will get there. More details about the prover will come next. And third thing that we need to move on is that we need full EVM equivalence. We are shipping a feature in the coming days that gets us almost there. It's called the EVM emulator, and you can think of it as an EVM interpreter written in Solidity running over our old Era VM. But this has some limitations and some performance costs. So we are committed to delivering native EVM equivalence. So BoojumOS is the answer to all of this. It's our fast EVM equivalent and customizable protocol. So let's look at the key idea for the new architecture. So the key idea is introducing an architecture with two separated layers. On top, we have the operation layer, BoojumOS, which is just a Rust program that implements the state transition function of the blockchain. As such, it's easy to modify, to customize, and upgrade without having to touch any of the proving part. On the bottom of this slide is Boojum2.0, which is the new blazing fast RISC-V prover that we're building. All of the details for the proving system will be presented by Michael in a little bit. So, in a nutshell, BoojumOS is a system-level implementation for the chain state transition function. The key point here is that it's system-level. We are putting a lot of emphasis on optimizing both of the layers that I mentioned before. A lot of people are putting a lot of work in optimizing the ZK proofs part. We are also doing that. But we also believe that we need to optimize the operation layer as well to get the most performance. So before we have a quick overview of the new architecture for BoojumOS, let's have a quick look at what the old architecture was. So here, as you can see, the protocol was implemented as a bunch of system contracts written in a combination of Solidity and Yule. And then it got compiled through our in-house compiler to this ERA-VM object code, which then got interpreted by two implementations of the interpreter, the one in the sequencer, what that we call the out-of-circuit VM, and the one in the proving system, Boojum2.0, which is the in-circuit VM. As I said before, we need to really make sure that these two implementations match, because otherwise we won't be able to prove what we commit to in the L1. So instead, we're moving to something that looks like this. We have all of our protocol encapsulated on top in the RISC program that is BoojumOS, and then we use the standard RISC compiler to compile it to two different targets: native x86 for the sequencing, and RISC-V for the prover. So after that, we use the RISC-V execution trace to prove it using our new prover Boojum2.0. So in this slide, you can see that now we have a unified implementation of the protocol, making things much simpler to customize and upgrade. So let's look at the main components in BoojumOS. So the first one is the system, which is a low-level implementation, very optimized implementation of the storage, memory, and I/O. The cool thing here is that we are providing abstract interfaces for all of these three functions: the memory, the storage, and I/O, that then are used by the upper components of the system. This is really cool because it enables us to offer really deep customization. So for instance, we can offer a chain to use a different storage model or use different oracles or whatever. Next is the bootloader, which is just a general implementation of the blockchain protocol. You can think of it as initializing a block, reading the transaction, validating, and executing the transaction. Thanks to the abstraction of the system, this is a really simple implementation that is easy to modify and add a new EIP or whatever. The bootloader, in order to call contracts, will call into different execution environments, which are our way to offer multi-VM support. So, as I'll talk a bit later, but we will offer different VMs, each of which will be able to call into the others, all seamlessly coordinated by the bootloader. So which execution environments do we want to support? First of all, EVM. We really need native EVM equivalents. The second one is ERA-VM, our old virtual machine, just so that old chains can migrate into the new system. Third, we want WASM as well, because we believe that this will open up the space to a bunch new developers that can write contracts in any different language that compiles to WASM. And finally, we want to have a RISC-V user mode execution environment as well. This will enable us to offer user-defined precompiles for very performance-bound and compute-heavy contracts. So yeah, you can think of this as someone writing a contract directly in Rust, compiling it to RISC-V, and running that for very compute-intense applications. So yeah, that was the introduction to BoojumOS, and now Michael will give an introduction to Boojum2.0.
Thank you very much, Antonio. So I work on the Boojum2.0, which is our new proof system, and I would like to dive into how we intend to power this, this new BoojumOS. So I'll start by describing what we prove, dig into the math, describe the proof.
Try this one.
Thank you. Yeah, as I was saying, then I'll describe the proving workflow for a realistic program, then get into the details of our comprehensive GPU acceleration, and close with some rudimentary benchmarks. Oh, actually, I lied. I want to open with a teaser of the benchmarks because we're quite proud of them. So these are the numbers that we're achieving for raw GPU proving speed on several different commonly available device types. And I'll get into that more later. So first of all, what do we prove? It's a reduced instruction set of RISC-V. So RISC-V I plus M base integer instructions plus extension for multiplication and division. Currently, we only support kernel mode for simplicity, although as Antonio said, we intend to support user-supplied Rust programs in the future. And we also require aligned memory accesses. And these are fairly common restrictions for industry standard RISC-V VMs. So the verifier, on the other hand, is under our control, so we can further optimize the necessary instruction set. So we don't need signed ops, we don't need subword memory accesses, and we don't need certain register-to-register ops, and this enables us to run the verifier a bit more efficiently with a smaller circuit. And finally, we have some custom delegation circuits, also known as precompiles, for common expensive ops. We've got Blake 2, big integer math, and some other experimental ones that we're working on. And we have an efficient delegation ABI that allows them to read and write the main circuit's registers in RAM without any expensive copies. So what is Boojum 2.0? From a bird's eye view, it is a Stark prover that proves error constraints that express RISC-V cycles. We use a maximum constraint degree of 2, which has the convenient feature that it turns out we only need one coset, one trace-sized coset worth of evaluations to evaluate all the constraints. And that means that for Fry, we only need the main domain, which we already have from generating the witnesses, plus one coset, which reduces the amount of FFTs and commitment folding that we have to do, or miracleization that we have to do. The underlying field that we use is M31, which is known to be very efficient on 32-bit hardware like CPUs and GPUs. And I've included a reference to a write-up from the Ingonyama guys that describes that in detail. And then for the degree 2 extension, we use the so-called complex extension with that looks just like a complex number that you're familiar with. And then we also have a fourth degree extension that we use for challenges for soundness, because we need at least 80 bits of formal security. And so for the NTTs, the number theoretic transforms, it turns out that this M31 has a bit of a catch. Its multiplicative subgroup only contains 1 power of 2, so it's not by itself an FFT-friendly domain. But there was a paper from Ulrich Hebach where he discovered this neat trick where the complex extension actually has a multiplicative subgroup called the circle group that does have a really nice FFT-friendly domain with lots of powers of 2. So, and it turns out that since we've expressed the secondary extension like a complex number, we can also use some 2-for-1 FFT tricks that are known from the FFT literature to do this sort of cool 2-for-1 process where we start with 2 base field valued columns, generate a pair of base field columns representing 1 complex column, and finally create our coset evals, which are also real. And then we can commit to real values instead of complex values, which is much cheaper. So some of you may wonder if this is a true circle Stark, which has also been quite famous in the literature recently. The answer is no, but it is fast on GPU, so we're shipping it. And if anyone's curious, I posted a write-up, which I will link at the end of the talk. So for our memory argument, we have this efficient construction based on 2 shuffles make a RAM. And there's a lot here. I kind of just threw it up here so that if anyone's curious, they can look it up and kind of get the idea. But the idea is that it all kind of fits together such that it only it's a grand product that can only multiply out to 1 if every read in the denominator cancels out the most recent write to that address in the numerator, which is exactly what you want from memory, right? You want your read to correspond to the read value that you pull to correspond to your most recent write. So our trace is roughly divided into 3 sections, which is the setup columns, which are fixed ahead of time per program and known to the verifier, and they contain the program binary, lookup tables, and these are like pre-committed before you actually run the program. And then we have the so-called memory columns, which contain RAM values and register values, as well as some of the metadata needed to delegate to precompile circuits. And then finally, we have the so-called witness columns, which are the bulk of the trace and just all of the other auxiliary values we need to prove RISC-V cycles. So for multiple segments, it turns out we can run up to 2 to the 22 cycles on typically available GPUs. So that's like 4 million cycles. But realistic programs require a lot more than that. So in such cases, we have to chunk the program into multiple segments. And loosely, in such realistic scenarios, we proceed in 6 phases. So we start with constructing the setup columns, like I said earlier, with the program binary and the lookup tables, which are fixed. Then we actually execute the program for our particular inputs to generate a RISC-V execution trace. And then we do what's called a memory pre-commitment to set up the memory argument, which I'll describe shortly. Finally, we generate the full witnesses. Then we can prove segments one at a time. And then we do recursive verification to combine the individual segment proofs down to one proof, which we can then wrap in a smaller start proof to submit to the chain. And this highlighted section here, the Stark witnesses and the segment proving, is the most computationally intensive part of the process. So for starters, for the setup, like I said, we just pre-commit to this program binary and lookup tables, and the verifier knows about this, and we can reuse this, we can cache this and reuse it across all runs of the same program. And then for the memory pre-commitment, the memory argument, the RAM, the RAM and register states obviously span the entire program. So it must be, known across segments, which means that in practice, we need to draw challenges for the memory argument that depend on the values of the memory columns across the entire program. So what we do is we pre-compute the memory columns, which in practice is only a small part of the whole trace. Then we pre-commit to them for all segments of the program, so for the entire program. And then from that combined numerical root, we draw challenges, which are then used for the memory argument. So in this way, the memory argument is consistent and sound across the entire program. And then at this point, the segments are fully parallelizable. We can do witness generation for the segments in parallel based on their particular chunks of the RISC-V execution trace. And currently we do this on the CPU, but we're planning to port this to the GPU soon. And finally, we get to sort of the meat of it, which is actually proving the segments. And again, this can be done fully in parallel on different GPUs even. And then for recursive verification, what we do is we take the segment proofs, we run one instance of the verifier over all of them, we collect the verifier's execution trace, and if we've done our job right, the verifier's execution trace is smaller, so it has fewer segments than the original program did, and so now we can prove the new segments, just like we did for the original program, and then hopefully that process will produce an even smaller set of segments, and we just continue that way until we just get a single proof that effectively verifies the entire program. So this is the part that is particularly interesting to me, which is an example profile of our of a sample job, and you can see that we're achieving pretty good GPU device utilization. GPU is the dark blue line is the GPU timeline. You can see it's quite well saturated with work, and we're also able to pipeline the next iteration's witness. I said earlier that the witnesses were being generated on the CPU, so we're pipelining the next iteration's witness copy to GPU. We're pipelining that with the previous iteration's proving work. So you can see we can keep all of the hardware saturated this way. Of course, it is, there's no free lunch, and we do need enough CPU cores to saturate, which for beefy GPUs can be quite substantial. But again, those big memory copies, as well as the CPU potential bottleneck, will be gone once we port witness generation to the GPU. So here's a close look at one iteration, and Google Slides kind of butchered this image, but you can still get an idea of how our workload breaks down. It's almost entirely in-house, hand-optimized CUDA end-to-end. We have our own NTTs, we have our own Blake hashing, we have our own fused kernels for lookup and memory arguments. We have our own kernels for the constraint eval, barycentric evaluation, deep quotient, as well as fry folding and queries at the very end. And also some utility functions like pointwise operations, transpose, bit reverse. And you can see from the highlights how the workload kind of breaks down across the timeline. So NTTs are kind of dominating, and then hashing is also, prominent. So with that, I'd like to close with some rudimentary benchmarks, and this is just the effective RISC-V megahertz that we're achieving for raw proving speed on the GPU. So, there's a lot of caveats here, and as I said, a real workload requires recursion, precompiles, potentially parallelizing work across GPUs, potentially a snark wrapper at the end. So there's a lot more moving parts, and we have these moving parts. We're still putting them together, but for the time being, I can highlight these very nice numbers that we're achieving for the proving speed itself on the GPU. And you can see in some cases, in some of the instances I tried, we were even bottlenecked by the rate at which we could move data. We were bottlenecked by the PCIe connection between the CPU and the GPU. So we literally couldn't move data to the GPU fast enough to feed it. Although again, witness generation on the GPU will eliminate this bottleneck. And why am I showing two sets of numbers? Well, another cool thing is that the first set of numbers, the gray bars, that's from Monday. And since Monday, my coworkers have been cooking and achieved 7 to 11% speed up in under a week. So we're still working. We're still even optimizing further relentlessly. And we would also like to do comparisons of this with as apples to apples as we can get with SP1 and RISC-0 at some point, as well as other leading ZKVMs. But we're doing a bit more due diligence to be sure that we're fair to all parties in such comparisons. So with that, I'd like to hand it back to Antonio to conclude and summarize.
Yeah, but we lost the slides, so I guess the QR code is not going to be very useful.
Wait, when did you lose the slides?
Just now.
Okay, thank God.
Yeah, don't worry.
Oh, man.
We can wait a second, otherwise I can just finish without the slides. But yeah, the conclusion is that great, thanks. That both BoojumOS and Boojum2.0 are key for the ZKSync roadmap that you can read in that link. And this comes in two axes. So the first one is that we need to improve the user and developer experience, and this is with the EVM equivalents and the multi-VM support. But the second axis is the performance, which is mostly given by all of the amazing work in the prover. And so, as I said, we target at the end of the year to have 10,000 TPS at around 1 cent of a cent per ERC20 transfer. So thank you so much. Here are some references that Michael mentioned, if anyone wants to take a picture. But that's it for us. Thanks again.
Thank you so much. Thanks, Michael and Antonio.